like most of us are here, so why don't we go ahead and get started. Question came up earlier about when our first in-class quiz will be. Our first in-class quiz will be next Thursday. Okay. It'll cover the material that we talked about today, Thursday of this week, and possibly Friday, depending upon how far we get. In-class quizzes, we'll talk more about those later in the week, but those are slightly more challenging than the online ones in terms of the content. Online quiz, there will be one posted this afternoon. Again, that's due by Friday at 5 p.m. So make sure you get on that as soon as you can. You have 3 attempts at that quiz. I only take your best one. If you're happy with the first one and don't want to take any more, that's fine. If you're not happy with the first one, don't just stop. Take others. Okay? I'm not going to penalize you if you do worse after the first one, but make sure you're at least attempting it. And let's see. If you have questions on any of the online quiz stuff, please come to me. We talked earlier, some people are having issues with entering answers and the computer system interpreting them incorrectly. If that happens to you, email me, talk to Jason, let us know so that we can look at it and figure out what went wrong and see, so we can keep track of these problems so that other people don't run into them as well. Right? But we can't change anything if we don't know about it, so you need to come to us and let us know. Right? If you have troubles in terms of you went through all this work and you submitted an answer and it just said wrong, and you have all this work that you went through and you don't know why you got it wrong, again, come see us. We can explain to you sort of the process that you need to go through. We can look at what you did and sort of identify what's going wrong. And then if necessary, we can award partial credit for the work that you've done to demonstrate that you're at least attempting the problems. Okay? All right. Any questions then before we start? Nothing? Sure. All right. Then let's go ahead and start. Last time we started 1.6. 1.6 is all about inverse functions and various aspects of inverse functions. We talked a little bit about graphs of inverse functions last time. We talked about procedures to find inverse functions. We talked about relationships amongst the domain and the range of inverse functions too. Today what we're going to do is we're going to talk a little bit about some of the algebraic properties of inverse functions, and then we're also going to look at some specific examples of inverse functions as well. But the first thing I want to talk about is the algebraic properties of inverse functions. Remember, this process of an inverse function is supposed to undo what the original function did. And if you think about that in terms of how functions behave together, if we take a function f of x, right? Suppose we have a function f of x and it has an inverse. Okay? Suppose our f of x has an inverse. Okay? If we take f of x and we compose it with its inverse function. Okay? Now, if we think about for just a moment, what is this doing? What is this composition of functions doing? Well, if you remember back, composition of functions is basically just saying, take the function on the right, the f of x in this case, and plug it in as the inputs to the f inverse function. When I do this, what should happen? Right? This is taking my input x and it's doing something to it, right? That's what f is. It takes my input x, it does something to it, and spits a value out. What does f inverse do to that value it spit out? It takes it back in and it undoes what that f of x function did, right? And so when we do this composition, what should we expect to get out? Not 1, not 0. We should get the x that we input now. It might be 1 or 0, but in the overall scheme of things from algebra, this should just give us the x that we started with back. Okay? Same thing would happen if I do things in the other order. Suppose I undo something first. Okay? This undo function, f inverse, goes first. And then I hit that with f of x. What should I get out there? This undoes something. This redoes it. What should I get out? I should still get my x out. These two properties right here are some of the defining characteristics of how inverse functions behave. Right? And when you're trying to verify that something is the inverse of another function, this is what you have to do to get that verification. All right? As an example, let's verify the functions here are inverses. The first one, f of x equals 1 over x. F inverse of x, also 1 over x. So verify that one. Number 2, g of x equals x to the third, g inverse of x, cube root of x. And then finally, h of x equal 1/2 x plus 1, h inverse of x, 2x minus 2. All right, so all we want to do is we just want to verify these are in fact inverses of each other. And the way we do that is we utilize these two properties over here. We do these compositions with these appropriate functions and make sure that we get this x value out. Right? So let's do the first one here. F composed with f inverse. What is that? Well, again, all I'm going to do, I'm just going to plug things in as I need to. So f of f inverse of x. What is that? That's 1 over, and then the f inverse of x is what I'm plugging in. So I'm just going to write that here for a second, f inverse of x, just to indicate that this is what the composition is doing. Okay? I'm plugging f inverse in for my x's. And now when I evaluate that, that's 1 over x. That's the composition, right? All right, well, I really don't like working with complex fractions like this. Let's simplify this down. 1 over x. How do I simplify that? Okay, what I can do is I can rewrite this. This is 1 over 1 times x over 1. Right? Property of fraction divided by a fraction. Well, simply multiply that out. That is x. I'm going to forego the opposite, the alternate composition because it's the exact same thing. In either case, this is what we're going to get. So I'll forego that one. But I really should, when verifying this, I really should do both compositions to make sure that they work. All right, let's try the second one here. Let's do g inverse of g of x. Okay. Again, all I'm doing is I'm taking my g inverse function, and instead of plugging x's into it, I'm applying this g of x function. So what is that going to look like? Well, if I write everything out in terms of my function notation, that's the cube root of what? What goes in here? This is where my x cubed goes. Alright? Now, if I need to, I can rewrite this in terms of exponents. A 1/3, or a cube root, is the same thing as a 1/3 power.
1/3. If you cube x, won't that cancel out the cube root anyways?
Right, and that's what I'm just writing that out here as a demonstrated process. I just rewrite the cube root function as a power. Now I can just use my properties of exponents, and that's x to the 3/3, which is just our x. Okay. Very good. And again, doing the other way is the formative process here, so let's do that. G inverse of x. In this case, what I'm going to do is I'm going to take something and raise it to the 3rd power. What goes inside the parentheses here? Inside the parentheses goes my cube root of x. Alright? And again, just fiddling around with the powers and everything. This is x to the 1/3 to the 3rd, which simplifies that down again. Alright, so those are in fact inverses of each other. And now we just need to do the same thing with the last one, verify this one. We'll do it one way, and I'll do the other one for you guys. inverse of h of x. If I do this, what do I get? Obviously, you know, I better get x out, but what would the next line here look like?
X plus 2 minus 2.
Close.
Or you have to work it out.
Right, I need to keep everything in
2
place.
times 1/2 x
Right.
plus 1.
Right, so I'm going to start with that. Again, just plugging the h of x into my h inverse function. Right. Now expand everything out here. Well, let's see, 2 1/2 is x plus 2 minus 2. Find out again. It's just the x. Okay. All right. So verifying functions or inverses. Pretty straightforward once we have the formulas. We have the formulas, it's easy enough to do, but sometimes it's getting those formulas that's the most challenging. All right. Okay. Not too bad, I hope. All right. Let's see. Now we'll move on to the new type of inverse. So you'll recall from last time that we can identify whether or not a function has an inverse by looking at its graph. That's one way of identifying whether a function has an inverse. One example of a function like that we want to look at is this exponential function. Y equals a to the x. Here a is greater than 1. Now, one thing you'll notice about this is, does this function have an inverse? Does this function have an inverse? Yes or no? Who says yes? 3 people say yes. All the rest of you are indecisive this one. Okay. Why does this function have an inverse? Okay, it passes the horizontal line test. An alternate way of saying that is that you'll notice this is an increasing function. This function is increasing everywhere. Okay, so it's automatically 1 to 1, which again, what it means to pass the horizontal line test. So this function has an inverse. Now, if we were to look at a specific example, an example of an exponential function like this would be 2 to the x. So we look at the function f of x equals 2 to the x. All right. Now, in trying to find the inverse here, we go through the processes of trying to find the inverse, the first thing we do is we write out y equals 2 to the x. And then we swap our x's and y's, so x equals 2 to the y. And now we say, all right, solve for y. Okay? How do we solve for y? How do we get y out of the exponent here? There is a process that we can go through. There is a special function that exists out there that allows us to do this. There are no simple little algebra tricks where I can't just take a square root or something like that. There's nothing simple like that that I can do here to get that y out of the exponent. But they did discover a function that does this for us. And those functions are collectively given the name logarithms. Logarithms are the inverse of the exponential functions. So, all right, so what are logarithms? What do logarithms do? Well, what logarithms do, what their purpose is their purpose is to tell you how to rewrite a number in terms of an exponential function. So what does a logarithm look like? Log a x. This is the notation we use for logarithm functions. Okay? I hope all of you have seen something like this before. Seen these kind of things before. Your calculator has buttons for something like this.